Wow. Okay, guys. So I have had one hell of an evening trying to get this thing to work, trying to sync audio and video and all this stuff. But I really wanted to work out this problem a little bit for you guys so you would know exactly how it's done. My sincere apologies for not getting this right um, earlier today, but I just want to explain a couple things that I didn't mention so you can be totally clear on everything. Now, the problem says that it's charged by being connected to a battery and is then disconnected. Okay, so that's really important. Um, the having a battery that's connected to a capacitor like that will store a charge on the capacitor. And if you disconnect it, you still have the charge. But these two configurations that you're looking at, if you were to separate them, are are two completely different things. And what the battery does is very different to what the capacitor, how it behaves on its own. I mentioned that there's a potential across this battery, which is very true. There is, and that would theoretically maintain itself in a circuit. But when you pull the plates apart, something really weird happens in that configuration. So I'm not going to explain that just yet, but I'm going to try to get to it. So this one over here, you are pulling the plates apart. Okay, so what you're doing there is you're increasing your distance. Your D is going up, right? So what's that going to do? Well, we know that capacitance is at least if it's got air or it's in a vacuum, it's epsilon naught times A over D. So if D is going up, then our capacitance is going down. We know that. So how does the electric field change? Well, what I screwed up was when I said that the electric field is K times Q over R squared. That is not true. That is for a point charge. That is not for a capacitor because a capacitor can be modeled as an infinite plate sheet of conducting charge. So, if you think of it as a big long sheet with positive charges on it, and you are going to make a reference point, say out here in green, then that's going to feel electric field lines from all over the plate. And it's an infinite plate, so it goes on forever, even though, I don't have enough space to accurately model forever. Sorry. But what's going to happen is that what happens when that we change that green spot? Let me back up a little bit here. And we make it farther out. Well, now your field lines are going to be weaker, but since you're seeing more of the sheet, you're higher up in the air, kind of like when you're up in an airplane, you see a lot more, it's just farther away. So it's actually going to still be the same thing. You go away, your electric field weakens, but you have more lines. So nothing actually changes. The electric field's the same. And the formula for that for a conducting sheet is, I believe it's sigma over epsilon naught. One of them is sigma over epsilon naught. The other one is sigma over 2 epsilon naught. I can't recall. It's on your exam one formula sheet. Take a look. Don't crucify me if I forget to put a 2 there, or if I put one there when how dare I, it doesn't go there. So when you pull the plates apart over here, you are increasing the distance, but that is not going to affect the electric field. So electric field does not change. E does not change. Okay, so what about potential? What happens there? What's going on with potential? We know that potential is the integral of E along a given length, and in this situation, that length is just the distance between them, right? So the electric field is uniform in a parallel plate capacitor, meaning it does not it's not affected by distance, as I already explained. So what does that mean here? Well, we're going to change the distance So if you simplify this, it's just E times L, or D, which we already defined as D. So, and that's going up. So this is 2 times as much. So voltage is going to double with distance, or change in potential. Okay. So what about energy? What's going to happen there? Well, this one's pretty simple once you have the other two, but be careful with the formula. So you know that potential is doubling with distance, and we're squaring that, right? So that's going to multiply everything, have a quadrupling effect on our energy. But what else do we have? We have C right here, and C equals, as I said, epsilon naught times A over D, and D is going, D is going up. So capacitance goes down. It gets cut in half. So if potential squared is quadrupled and capacitance is halved, then our energy is doubled. Okay, so U equals 2x. So that's that problem. Now, what I was saying I wanted to cover with the battery, weird highlighter, is that there is a potential across this battery here. And when you charge this capacitor up, it's going to have that same potential on it when the charges build up. It's supposed to be on the bottom plate, sorry. So when you pull this apart, you're going to do something similar that you do in this problem, but you're actually going to have to work against the battery because the battery has an internal resistance in it. And that's something that we're not quite covering yet. We're getting ready to, but you're probably going to actually have to pull harder to make that happen because the battery has its own resistance to it, which is going to resist the work that you're doing even more. And you will force a potential on the battery. You could potentially cause some damage to it. But I think that's what would happen there. But that's why they said what happens when you disconnect it from the battery, because now you don't have a potential absolution there that's going to fight you pulling the plates of the capacitor apart anymore. So I hope that makes sense. Sorry I screwed it up. I hope I made you study in my error, but I will try to limit the unintentional errors nonetheless. That's all. Email me if you have any questions. Thanks.